Thanks everybody for showing up. We appreciate your interest. Today we have a great talk. We have Dr. Peter Rose who will be talking about running notebooks on high performance systems and scaling up your projects. So he'll talk about that. It should be very interesting. Peter's got background in bioinformatics and 3D visualization and big data technologies, and a lot of interest in reproducibility in scientific research and making notebooks run better. So with that, I'll turn it over to Peter.
All right, thank you, Mary. Let me share my screen here. All right. So I have been using Jupyter Notebooks a lot in my research, and one thing I try to do is when I set up notebooks to make sure they run anywhere. That means on your laptop, be it Mac OS or Windows or Linux, and then also be able to scale it up so it actually runs on a supercomputer such as Xpand. So that's what I'm going to talk about today. So here are some of the objectives for today. So I will show you how to set up a reproducible and portable software environment. And then we'll go to the Xpanse web portal where you can check allocations, job status, file management, and you also can get a terminal window there. So actually the entire session from today, I will run through a web browser. Then I'll show you how to run JupyterLab on Xpanse. And then we want to take advantage of Xpanse by running on multiple cores or running on GPU. And then finally, if you want to go into production, you can also run your JupyterLab in batch mode on Xpanse. And then finally, if you don't have an Xpanse allocation, I will briefly talk about how you can get an account, a trial account on Xpanse. But before we get started, let's talk about, when does it make sense to run your Jupyter Notebook on Xpanse? So when I do coding, I usually do that on a desktop or a laptop. That's a much more convenient environment for editing. So if you're in the exploratory phase of a project and your data is small enough, you can, do this, on your laptop first using small data set, and you can either run it on a single core or just a few cores. But then at some point, you reach a point where you want to run this on larger data sets or runtimes are too long. In that case, it might be time, to try to run your notebooks on Xpanse, where you can then run it on many cores in parallel or run on GPU. So, if your application just runs on a single core, it doesn't really make much sense to try to run it on Xpanse unless maybe you want to use a GPU. So you really need a use case for running on Xpanse. Okay, so just a quick overview of Xpanse itself. So Xpanse has two types of nodes. First, it has compute nodes, which are GPU cores. Each node has 128 CPU cores, and we have 728 of those GPU nodes here. Important thing to know too is that each node comes with a fast flash drive. So a lot of your work, if you have intermediate files you want to do on this local flash drive on a compute node, and I will get into more details on that. Then Xpanse also has 52 GPU nodes, and each GPU node has 4 GPUs and 40 CPU cores. And again, it has a local flash drive attached to it as well. So we will be using those two types of nodes, for running Jupyter Notebooks. When you run jobs on Xpanse, you need to choose a partition. And here a number of partitions, and I highlight a few partitions that are useful for running Jupyter Notebooks. So if you run a Jupyter Notebook on CPU, you generally want to use a shared partition. And that means you're running a job with less than 128 cores on a single node. So that's a good one to run Jupyter Notebooks on. And if you use a Jupyter Notebook with GPU, the GPU shared partition is a good one. Again, that's on a single node with fewer than 4 GPUs. Now, if you want to do some quick testing to see if things actually work and not do production runs, you can use, for example, the debug queue for testing for very small jobs to try something out. there's a maximum wall time of 30 minutes to run. And if you want to test out some GPU code, you can do that on the GPU debug partition again, that only runs for 30 minutes. Okay, so how do you set up a reproducible and portable software environment? I mean, first of all, why? As you probably know, there's a problem reproducing other people's work, being it in a lab, but surprisingly too, a lot of computational research is not reproducible. And how can we change that? So there are a number of tools that help with that. Obviously, this is why we're here today. We're talking about Jupyter and Jupyter Notebook. One nice thing about it that the Jupyter Notebook combines documentation, code, and results. So you really have a description of your code, not just the code itself, but you can actually read the documentation, see the results it produces. So that definitely helps with reproducibility. Then you need version control, for example, Git and GitHub as a repository for your code to share your code and version it. And then today I will talk more about how to create an environment, a reproducible environment on your computer or on Expanse. And there are two major ways of doing it. One is using Conda, which is an open source package. You may have used that to install software, but it's also an environment management system. And then on the more sophisticated side, there are Singularity containers that you can run on Expanse. And then finally, now we have Expanse, the hardware to run it on. Okay, so just a quick comparison of Conda versus Singularity, in case you're not familiar with that. So with both of them, you can create a reproducible environment. Conda is best for beginning users, or if you already have experience using Conda, where with Singularity, you probably want to be a more advanced user, may have some previous experience, such as Docker containers. Conda is good for exploratory development. Let's say where you do frequent changes, maybe add new dependencies and so forth. And it's also easy to compose an environment where you combine many different packages together. On the other hand, Singularity is often set up for a single tool. And for example, SDSC provides optimized containers for a number of applications such as PyTorch, TensorFlow, and so on. Now, with Conda, generally you can only run them on a single node, and that means up to 128 cores. If you want to do more, you probably want to use a Singularity container, which may have set up in a way it can run on multi-nodes. Conda is really supported anywhere, so that's why I like it. Runs on your laptop and anywhere. Singularity only runs on Linux. If you run it on Mac or Windows, you need to install a virtual machine to run it. A nice thing about Conda is it runs on your native operating system, so it integrates with all the other tools you're using. And Singularity, basically, you package the entire operating system, such as Ubuntu, into the entire container. So today I will focus on Conda. And we have separate webinars about Singularity that have been recorded, so you can go back if you want to learn more about Singularity containers. But today, the focus is on Conda. So what does Conda do? Let's say you do 3 types of analysis here, and they have different environments, different software environments. Then they can be completely separated. They don't interfere with each other, but they can run on the same hardware. And then at some point, maybe reach a point where you want to productionize it. That might be a time then when you either use, on HPC, you would use a Singularity container. Maybe on other systems, you could use a Docker container. Okay, so what is Conda and why to use Conda? And that comes back to reproducibility. One major reason why code fails or you can't run other people's code is, and that's this 4th pillar here, that's the environment. The environment either has not been described or set up properly. In which software you're supposed to install, how, which version, and so on. So that's what I'm trying to address here today. You may have used Conda already to install packages such as NumPy, Pandas, and etc. And one thing Conda does, it checks dependencies. So it makes sure that all the packages that you install, that they're compatible with each other. But Conda can also manage your environment. You can create multiple environments on your system, and they can coexist at the same time. And I will show an example of that. And as I mentioned, it runs cross-platform and it supports many different languages. So why use Conda environments? A beginning user, I'm talking about Python users, they typically do this. They have Miniconda or Anaconda installed, and then they need a few other packages, and they use either pip or Conda and start installing some packages here. But down the line, you will have some problems with that, because you will have version conflicts, you will get errors, and your results may not be reproducible. Now with a Conda environment, I can have multiple environments coexist on the same computer. I could, for example, have one environment that uses Python 3 and a particular version of Pandas and scikit-learn, as well as another environment that uses a different version of Python and different versions of Pandas and scikit-learn. So they can coexist without a problem. Plus, those environments can be now ported to other platforms, for example, from your laptop to Xpand. So that's the other advantage of using Conda environments. How do you create a Conda environment? The best way to do that is that you create a file called environment.yaml or YML. And Conda environment file looks like this. First, you give it a name. And my recommendation is that use the same name as your Git repository name if you use Git. So for example, today I will use this Git repository called df parallel. So I also use the same name for the environment. So I don't need to think about that name. Then I need to say, okay, the dependencies, where do they come from? So there are various channels available, such as Conda Forge and Anaconda. Usually Conda Forge has the newest versions available. And you may need to add other channels depending where you find your packages, such as Bioconda or NVIDIA, etc., etc. Then you specify the dependencies that you have. Let's say I want to run Python 3.8, JupyterLab 3, and then I have a few other dependencies like Dask and PySpark and so on. To make it reproducible, it's best to give it a version number here, and it's called pinning a version number to make sure it's reproducible down the line. And the nice thing about Conda is you can not only install Python packages, but also other types of software. So for example, I'm using PySpark here, which needs the Java JDK. So I can also install Java. For example, here I'm installing Java 8. Although I have Java 11 installed on my machine, but since it's an isolated environment, I can have multiple versions of Java coexist. Another thing you can do in Conda environment, and this is a less known feature, is you can set environment variables here. So for this particular Git repository, I needed to set some logging information. So I set up an environment variable, which is a path into some configuration file. So if you have any configuration options that work across platforms, you can already set them up here. So the user doesn't need to remember to set them up here. Okay, so how do you create a Conda environment? A prerequisite is that you have either Miniconda or Anaconda installed. So that's the first thing. We recommend using Miniconda since it's more lightweight. And then, once you have your environment.yml file defined, you create a Conda environment by saying Conda environment create and use the file environment.yml. And if you want to list your existing environments, then you can list them this way. And now let's say you want to do some work with a specific environment. You say Conda activate and give it the name of the environment. And then you're ready to start your work. Then you would start JupyterLab, do your work. And then when you're finished, you say Conda deactivate to deactivate the environment. Now this all works fine on a Mac, Windows, Linux, as long as, if you run on your own small machine or desktop or little server, that works fine. But this scheme does not work well on Expanse, because on Expanse, your home directory is on a network file system. So it will be extremely slow and it will interfere with network operations. So don't do, this is what you want to do on your own computer, but you don't want to do that on Expanse. Instead, we have a script called Galileo, and that will take care of doing all this for you. So, don't do this on Expanse, but use the Galileo script, which I will talk about in a few minutes. Okay, so today I also want to introduce the Expanse portal, and that allows you to check, what allocations you have on Expanse, job status, file management, and you can even get a terminal window. Actually, today, all my demos will be done just through a web browser. Okay, so this is how the Expanse portal looks like. So let's actually go to the Expanse portal at this URL. So I've already logged in. You need to log in here with your Expanse password. And the first thing you may want to see is, what is my allocation? So down here, we can look at allocations. So here are my allocations. So I have one allocation. This is the account number or project number. So this one is very important as you submit jobs. You need to know this number. And I have 5,000 service units or hours available, and I have used up to 153. And so this is the expense. Then for GPU, the accounting is separate. So for GPU accounting, you see same project number, but I have 250 GPU hours available or service units available for GPUs. That's how you can check your allocation. You can also access your home directory from here. So here you see all the files I have in my home directory. And it's very nice feature is that you can easily upload and download files into Expanse here from your local computer. So this is very convenient. We can check the job status, which I will do later once I run jobs. And you can also get a terminal window and use it right from here. That's a little introduction to the Expanse portal, and I will come back to it later as I do a demo. All right. Okay, so we talked about the Expanse allocations, and yeah, this shows, if you have active jobs running, it will look like this. You see your jobs. Here's one job that has just completed and another one is running. And you can also delete or terminate a running job here if something goes wrong. All right, so that was a little introduction to the Expanse portal. Let's talk about running JupyterLab on Expanse. And as I said, you don't want to create a Conda environment in your home directory, but rather use the Galileo script. And this script launches a JupyterLab or Jupyter Notebook on an HPC system. And it establishes a secure connection between the notebook server and your web browser. So this is important for us, that because generally, Jupyter, if you run it, it runs on your local host under HTTP, which is not secure. So we have established a way to run this in a secure way on HTTPS. To learn more about Galileo, we have excellent documentation here. So Marty Canvas, who is online here today too, he developed the Galileo tool. So there's some very nice documentation available here. And you can also look at Marty's webinar about using Galileo and Singularity containers as well here. Okay, so how do you actually run now JupyterLab with using Galileo? First, you need to add a path to Galileo, and that's this path here. So you can either run this export command on your shell window, or if you use it a lot, maybe you can add it to your batch profile file. So it's always available. So once you set up your path, then you can run it. And this is a typical command line, how this looks like. So you say Galileo launch, and then you say the account number. Remember when we looked at the Expanse portal, that's how you get your account number here. And then we talked about partitions. So if you run on CPU, you generally want to use that shared partition and say, okay, I need 10 CPUs and 20 gigabytes of memory. So this is in gigabytes. I want to run it for 30 minutes. And the name of that Conda environment, in this case, is called DF Parallel. And this environmental.yml file is located at this particular path, my home directory, DF Parallel, and that's where this is. And then we add another option called member, which I'll talk about later. So once you do this, you will see that it generates a URL for you. It prints in your terminal window a URL that looks like this. And then you paste that into your web browser and it will then establish a Jupyter Notebook session. So how does this work? So once you paste this URL into your web browser, this status bar comes up and it goes through 4 steps. First, it needs to be getting into a queue. Then it starts running, it creates some token, and eventually it establishes some proxy. And then it will show, then your web browser will launch with this URL that I showed you before. You can then, run your Jupyter Notebooks on Expanse. And here's one important thing. When you are finished with it, you want to go to the File menu, which is shown here, go to the bottom and click Shutdown. Don't just close out the window here, but shut down Jupyter Lab. And that's important because this will actually terminate the process. If you don't do that, the process will keep running and using up resources. Okay, so let's talk a little bit about how to scale things up using either multiple cores on a multiple CPU cores or using GPU. And I created a small example for that. Many of you, if you're using Jupyter or Jupyter Lab, you're probably using Pandas data frames. So I thought I'll give you an example how we can scale up large tabular data sets. So what you would typically do if you use Pandas data frame is you load the entire data set into a Pandas data frame. But the problem is with large data sets, this is your available memory, and this is how much memory you need. So the Pandas data frame doesn't fit into memory. So how can we deal with that? Instead, we can use a different library, which is very similar to Pandas, called Dask. And we can use a Dask data frame. And what it does, it splits up this large data set into smaller, what's called partitions. Each of those partitions then fits into memory. This is, so you can process any kind of very large data set, doesn't matter how large they are, because they're broken up into smaller partitions, which then run on, Expanse. And then secondly, that also serves a second course. We can then run things in parallel because now you have multiple partitions here. Those partitions can then run in parallel on multiple CPU cores. And the Dask data frame, unfortunately, only supports a subset of the Pandas API, but most of it. So this is a good way if you're dealing with very large data sets that don't fit into memory. You can instead use a Dask data frame that splits it up into pieces, plus it runs in parallel. Okay, but we can also using GPU. So this almost looks identical, this slide, except instead of Pandas data frame, we use CUDA data frames developed by NVIDIA, and those are GPU-powered data frames. But this has the same problem as, your data sets get larger, they still don't fit into memory. And again, this is where Dask comes to the help, where we can again use Dask to split this up into partitions and then run, very large data set on GPU. And again, Dask CUDA-DF only supports a subset of the Pandas API. So this is an example how you can scale things up either using multiple cores or running this on GPU. And this is the example I will show you today live. Okay, so I created a example Git repository for this webinar. It's called DF Parallel for parallel data frames. And we're gonna have a few notebooks here where we read a large data set. First using Pandas, Dask. I didn't mention Spark. Spark is another distributed framework for running large data frames. Then we run CUDA-DF, which runs on GPU, and Dask CUDA-DF running also on GPU. As I mentioned, the problem with Pandas is it doesn't run in parallel. It runs on a single core, and it cannot run out of core. That means, all the data need to fit into memory. With Dask, we overcome those issues as well with Spark. CUDA-DF also has it runs on GPU, but again, it can run out of memory with large data sets. Again, CUDA-DF comes to the help, and you can run anything, any size on GPU. Okay, so how will we run those notebook examples? So it would work like this. First, you clone this Git repository. Then to run it on CPU, we can then run the pandas, Dask, and Spark data frames. And this is a launch command, as I've shown you before, with account number here, shared partition, 10 CPUs, 20 gigabytes of memory, 30 minutes. This is the name of the environment, and this is the path to the environment.yml file, and that's Mamba, which I'll talk about later. Now, if you run it on GPU, it's slightly different. You would instead choose the GPU shared partition here. Again, 10 CPUs. In this case, we're choosing 93 gigabytes of memory and 1 GPU. And the rest is pretty much the same, except the environment.yml file. I have a different one, which now includes some of the NVIDIA dependencies to run the CUDA data frames here. So this is how you would run this, and I'll show you that live in a minute or so. But let's talk about one more thing, and that's about, it's called packed Conda environments. When you run this Galileo script, what it does, it creates a Conda environment on the fly. And as many of you know, Conda is slow. So how can we deal with that? First of all, we can use this Mamba option, which is basically a drop-in for Conda, but it's much faster. It's 50 to 80% faster. And Mamba, if you look at Wikipedia, is described as a fast-moving, highly venomous snake. And that's kind of what it is. It speeds things up. So this is a very nice name for this particular solver here. So this is one way. So if you use this Mamba option, it will speed things up probably at least twice as fast. So that helps. But let's say you use this environment every day. You don't want to rebuild that Conda environment all the time. So what you can do instead, you can create a packed Conda environment. A packed Conda environment can be moved, for example, from your home directory to a Scratch directory on the compute node or vice versa, where if you have a regular Conda environment, you cannot move that around, it will not work. So that's why we need that one more step, which is packing it. There's some limitations. So if you have Conda and PyPy dependencies all in the same environment or YML file, sometimes that does not work. Okay, so how do you create a packed Conda environment? So actually yesterday evening, I wrote a small script to make that easier for you. It's a little bit experimental, so it may not always work, but you can download that script with this wget command, you make it executable, and then you say, okay, pack.sh, you give it your account number, the name of the environment, and your environment.yml file, for example, this GPU YML file. And that will create a packed Conda environment, which you can then reuse. What it creates is a file called, in this case, called dfparallel-gpu.tar.gz. So it creates a tarball of your Conda environment. And then to run it, you again have your Galileo script here. Pretty much everything is the same here, but instead of giving it a Conda YML file, you say Conda pack, and you give it the path to the packed Conda environment. So that speeds things up dramatically. If you want to learn more about all the details about Conda environments, please go to this Git repository that has the detailed comments about how to use Conda environments. Okay, so let's go to a demo here. So this is a demo I'm gonna run here. So I'm gonna run this on a GPU partition with 10 CPUs, 93 gigabytes of memory, and 1 NVIDIA GPU. So let me copy this here. And let's see, let's go back up here to our Expanse portal. So here's the Expanse portal, and you can see I can access a shell command here. So this is my home directory on Expanse. So here are my files. So I just paste this Galileo command here. So I say, okay, this is my account number. You won't have a reservation. I have this only here today to make things faster for the demo. Run it on GPU shared, 10 CPUs, etc., etc. So let's run this. So it shows you, the input parameters here, and then at the bottom, it shows a URL. So take this URL at the bottom here and paste that in a web browser. Going up here. Okay, so it takes a little while. First, it needs to get into the queue. Hopefully this doesn't take too long. So we're just waiting for this last step where it sets up a proxy to the web browser, and then hopefully it's going to happen in the next few seconds here.
Hey, Peter, there's been a tremendous number of questions, but Marty's doing a pretty good job of fielding them.
Okay.
Just so that you know, there are some great questions, though.
Oh, great. Yes. Yeah,
You
maybe
can look at
yeah,
you can
okay,
look
maybe
at
I
one
can
and
look at a
answer a couple
few.
if you want to. Go ahead.
Yeah, okay. So let's
Yeah,
see.
Peter, I have one while you wait. I've been sort of following ones I didn't answer.
Yeah.
Well, so the first one maybe I sort of commented on, but one question came from Eric asking, why do you recommend a Conda environment over, say, like a pip virtual environment or something like that?
Yeah, one of the reasons is that with Conda you can also install non-Python applications such as Java and so on. I'm not sure if you can do this with PyPy as well, but that's one reason, Yeah.
Sure. Yeah, I think that came up in the chat.
Yeah. All right, so maybe let's continue then, and maybe I can answer some questions later. So you see the notebook came up. So this is, okay, let me go back here. You see the URL up here. So that's, the URL that originally pasted here. So let's go through this here. So first we need a data set to download. So I have a notebook here that downloads the data. So let me just run this first, and then I'll explain what it does. And let me see, let's go into presentation mode so you can see this better. Is this large enough? So what this notebook does, it downloads some gene information from the NIH, and it basically downloads this file here from the NIH. One thing I do if I want to make sure that the code runs across platforms, it runs on Windows, Mac, anywhere, I don't download, let's say, using wget, which would have been easier, but instead I wrote some Python code to download that, as well as I need to unzip the code, and I do that in Python. So this code will run everywhere. That's why I'm not using shell commands to do that here. So that's something to keep in mind if you really want to be able to run this cross-platform. So I downloaded that file. This file is 5.4 gigabytes. And now let's read this into various data frames. So we'll start with the pandas data frame here. Okay, let me close this. So this doesn't do anything exciting here, except it reads the file. So one important thing is when I downloaded the file, I download that into a Scratch directory, which is shown here. And that is on the node. So the node has a flash drive attached to it. So this file has been saved on the flash drive. So now I have really fast access to it. And there's an environmental path called local scratch dir, which is set up by Galileo. So if you use that, then that's how you know the path to your local scratch directory here. So we don't do much exciting here. We read this into a pandas data frame, and instead of reading all the columns, I give it only a set of columns here. And then we just do a few simple operations here. So first we say, okay, there's gene information in this file. Give me only the genes where the type of gene is protein coding. So we do some filtering here. Then we are grouping by taxonomy ID, which is the organism. So we group the genes by organism and we count them. And finally, we sort by that count. And then we do a few queries. For example, we find out that there are about 20,000 human genes. And those genes are the top genes that have top organisms that have the most genes here. So, but I don't want to talk about the biology here, but this took 54 seconds in Panda. So it's still right. It didn't run out of memory because for this demo, I didn't want to use a huge data set. It would take too long, so this is just 5 gigabytes. So it's not really big data, but this is just for demonstration purposes. Okay, now let's do the same with the Dast data frame. As I mentioned, Dast breaks this file into smaller pieces or partitions, and they are processed in parallel now. Basically, the code looks almost the same. The API is slightly different in for Dask, but most of it, it's pretty much identical here. And again, let me run this here and see what we get. We do get the same results, but let's see how long it takes to run this. Okay, so with Dask, the same task took like 22 seconds. So we went from 50 something seconds to 22 seconds. Now this is pretty much limited by IO, because this is where most of the time it's taken up reading that CSV file, so that's why you don't scale as much as you thought I would, because it's really a little bit IO bound process here. Okay, let's close Dask and Pandas. Now we use Spark. Spark actually runs on the Java virtual machine. And the syntax for Spark data frames is slightly different, but it's pretty much the same thing. You read a CSV file, you do some filtering, grouping by sorting. And at the end, I actually convert that to a Pandas data frame. And let's see how long that takes. Okay, so it's a little faster. So 14 seconds, which is not bad, for a 5 GB data set, reading it and doing some simple data manipulation on that. All right. Okay, now let's run this on GPU using a CUDA data frame. Again, the syntax is pretty much the same as we had before for the Pandas and Dask data frames. So there might be some small differences. So that's much faster, 3.5 seconds. So that's not bad, on a single GPU. And then finally, no, the Conda data frame, the CUDA data frame works fine with smaller data sets, but if you have really large data sets that don't fit into memory, it will not work. In that case, the Dask CUDA data frame, which is this, and it's very easy to use. Instead of CUDA-DF, you read your file with Dask CUDA-DF, and that's, I think, the only change you need to make to your code. And let's run this. So it was a lot slower because, it needs to break up this file into multiple partitions. So there's some overhead running this in parallel here, but it will work for very large data sets. Okay, so that was a few simple use cases, how you can either run things in parallel on CPU using Dask or Spark, or run it on GPU using CUDA-DF or Dask CUDA-DF. And the changes to the code are minimal. If you're used to Pandas, you can very easily upgrade your code to run in any of those environments. Now, one important thing is, and I mentioned that before, when you're finished with your job here, you want to not just exit out of the browser here, but you want to go to shutdown, and that will shut down your process here. So let me shut this down. And let's go to the Expanse portal again, and let's look at the job status here. And you see, this is a job I just ran and I just completed here. But here you would also see any running jobs you have, and you can also cancel any running jobs through this portal here. So as you see, it's very simple to run things on Expanse using the portal. And I didn't even have to go to SSH into the machine. I can do this all from the web browser. Okay, so let's see what's next. Okay, so that example that I showed you was just 5 GB. So what I did, I made 4 copies of that file and create a larger data size, 21 GB. And if you look, this is on disk size, but if you look in Pandas, actually, if you look at the Python objects, it will take up 62 GB. And here's a comparison, with a data set that's 4 times as large. Pandas took 222 seconds, Dask were about 5 times as fast, Spark 7 times as fast, CUDA-DF ran out of memory, couldn't do it, But Dask CUDA-DF is able to do that in 11 seconds to basically read in 62 GB of data. So that's pretty good. Okay. Now, maybe you come to a point where, okay, your Jupyter notebooks work, but now you need to scale it up even more. Maybe instead of running it on one input file, you want to run it on on 10 input files, you don't want to do that manually. You want to run this now in batch, and you can run your JupyterLab also in batch, and I'll show that next, how that works. There are various ways you can run JupyterLab in batch. One way I like to run this using an application called Papermill, which was developed by Netflix, and it can do a couple of things. First, you can parameterize the notebooks. That means you can pass in arguments into a Jupyter notebook. Let's say you have some machine learning problem and you do some grid search. You could pass in some parameters as arguments into your Jupyter notebook from a shell script. So that's one thing Papermill can do. And then it can also execute the notebooks. And this is a snippet that I cut out of one of my scripts here. This is the way it works, is I have a directory of notebook files. I loop over all the notebook files and then say run Papermill with that notebook as input. And then it creates an output file, which is also a Jupyter notebook, but it's the executed Jupyter notebook with all the output in it. So this is a very easy way, if you have 50 notebooks or you need to pass in parameters, that's an easy way to run this in batch. And I provided you 2 links here, to run the notebooks in batch using CPU and GPU. They're a little bit ugly, those scripts. So you may, if you want to use it, just copy and paste things out of here. So if you want to run things in batch using the sbatch command on Expanse, so you need to set up some parameters. Again, you need to put in your account number here, which partition you want to use, GPU shared, how many nodes, 1 node, 10 CPUs, 1 GPU, 93 gigabytes of memory for 15 minutes, and maybe the name of that job here. Then to set things up, you need to do a few things. If you run on GPU, you need to load a few environments, including Slurm, which is the queuing system, and you need to load the GPU environment. Here we need to set up, okay, what's the name of your Conda environment? Where's the YAML file? Where is the notebook directory, and where you want to put the results? I'm going to skip over the code in the middle. That creates the Conda environment on Expanse. And then the important part is on the bottom here. This is now where I loop over all I CD into this notebook directory and make a result directory, and loop over all the notebooks and put the results into this results directory. And then when your job finishes, you can look into the results directory and have your results in there. So that's an example or a template, how you can run JupyterLab in batch. Okay, so now that I talked to you about all of this, and let's say you don't have an Expanse account yet, and you thought, oh, I want to try to run my notebooks here. So there are a number of things you can do. So first of all, Expanse is an Exceed computing resource. So your Expanse allocation goes through the Exceed portal. So you can apply for a trial account by going to this URL. And I believe you get 1,000 CPU hours and also some GPU hours for a trial account. And then, as you get familiar with that, and you then submit a proposal to get a larger allocation on Exceed and run your jobs here. And that is the end of my presentation. And I want to acknowledge, first of all, actually I forgot to T here, Marty Candace, who was really helped a lot. He developed that Galileo script, Mary Thomas, Scott Sakai, Rob Zinkowitz, and this was funded by the NSF as part of our cyber training grant. And with that, I'll take any questions. So maybe, can somebody, Marty, maybe you want to tell me about some other questions that came up that I...
Yeah, there's a few that I left on the side for you to answer at the end. So one earlier in the talk came from Guillermo. He asked have you found any issues when moving Conda environments across platforms?
Yeah. So I'll give you an example. Let's say I have an environment that includes those CUDA dependencies. They're not available on Mac, for example. So you cannot create a Conda environment using those CUDA environments because they are not available. So that's why, for example, I have 2 different environments. One is a CPU environment, one is a GPU environment. So that's that's one example, where things are not exactly transferable because you don't have the right hardware, So some packages only work on specific hardware. Those obviously cannot be ported, I think that's probably one of the major issues I see, but there's really no workaround there. Hope that answers the question.
Yeah, yeah, I think that helps. There was some discussion in the chat too, but the next question that I have on my list here is from Dimitri. What is the best way to apply version control to Jupyter Notebooks?
Yeah, I mean, you don't want to version control the Jupyter Notebooks, but you want to version control the dependencies, and that's what I was showing. And let's see if I can get back to the early slide here. So where you define your environment.yml file, that's where you specify the versions that you're using. Let me see if I can get back to this slide here. It's a little slow. Yeah, let's see. Ah, here we go. So, this is where the version control comes in. So I say, okay, we use Python 3.8, and this is important too. In your Conda environment, you need to include, for example, Jupyter Lab, because Galileo, that script does not know anything about Jupyter. So this is required to run this on Expanse. You need to include this here. But see, this is where I specify the version here. Hopefully that helps.
Actually, I was asking about the version of the notebook, not the Conda environment.
Yeah, that's this one here. So I'm using Jupyter Lab version 3, so that's the Jupyter Notebook or Jupyter Lab version.
I mean the code of the notebook, not the version. The code that you execute, you change this after you execute.
Oh, yeah, right. I mean, that is in my Git repository, So yeah, okay, maybe I should just show you this one here. So GitHub takes care of the version control, and as you probably know, it's a little bit difficult if multiple people work on the same notebook. There are some issues with versioning Jupyter notebooks. There are some tools like NBDime and things like that that can take care of that. But you're right, there are some issues with versioning Jupyter notebooks. Does that answer your question? So by the way,
thanks.
So by the way, this is, this Git repository that we were using here. So here's your environment.yml file. Here's one for GPU. And the one for GPU has additional dependencies here, like CUDA, Dask, and CUDA tools, as well as new channels here, like the Rapids AI and the NVIDIA channel here. So those are not available, let's say, on a Mac. And therefore, I have a second environment.yml file. This is the one that runs on CPU, so this should be run anywhere, but the one with GPUs will not. No. And all the notebooks are in here. All right. Any other questions?
I guess I'm wondering about Dask CUDA data frames. Do they work well with MPI for spreading across multiple GPUs and multiple nodes? How would you do that?
Yeah, I don't think that will work with the Conda environment. I think that's where you want to use a container if you go across multiple nodes. So this just works, in a single easy environment. If you need to have any other configurations set up, that probably will not work.
Okay. The second question is, would it be possible for me to adapt Galileo to use a Python virtual env instead of Conda if I wanted to set that up for myself?
Yeah, I mean, I can let Marty answer that question since he wrote that call.
Yeah, there's no issue with that. I mean, basically, if you don't use some of these flags, it'll just assume that your environment's set up in your shell, like by default.
Sounds good. That was a great talk. Thanks for giving it.
All right, any other questions?
Peter, there's one that just came in. What is the advantage of using Dask versus Spark?
Yeah, so if you're already using Pandas and know the Pandas API, then it's much easier to use Dask because it's very similar. Dask implements a subset of the Pandas API, so that's the major reason you want to use Dask. Also, Dask is a complete Python solution, so it's actually easier to use. Spark is a little more complicated, you know. So there's a wrapper called PySpark that wraps around Spark. Spark is written in Scala, which runs on the Java virtual machine, so it's a more complicated. So you need to, you know, for example, it has dependencies on Java that I set up here. You see it's using Java 8 in this case here. So it's a more complicated setup, Spark. Also, the syntax is not as user-friendly, at least I find it more difficult. But there's a new thing called pandas on Spark. So, you know, the Spark folks noticed that everybody's using pandas. So they're also now creating an API, which is pandas-like, although I have not used that myself yet. So one thing about Spark is, you know, it's a little faster than Dask, and, you know, it's just a more complex system. You know, if you really have very large data sets, let's say terabyte or petabyte data set, maybe Spark might be a better environment. But if you have, you know, small, medium-sized jobs, then maybe Dask is a better and easier option, in my opinion.
Another question, maybe this person missed it, but how do you request access to Expanse? Can you show that again, Peter?
Yeah, right. So let's see, let me just get out of this. So first of all, you can get a trial account, which gives you 1,000 CPU hours on Expanse by going to this. And that goes really rapid. I think you can get that probably in a few days. And then as you get familiar with the system, you want to think about, you can submit a small proposal to exceed and get a larger allocation there. I think you can get also a startup account there with 50,000 hours of CPU and 2,500 GPU hours then. So let's go to one of those URLs here. That's how you get access to Exceed, and it's free.
Peter, I also posted a link in the chat with a link to the Expanse user guide, which also gives you instructions on how to get an account.
Right. All right. Any other questions?
Oh, I just also wanted to ask people to send us requests for types of topics you would like to hear about in the next year. We'll start planning our end of 22 and 2023 webinars, workshops, boot camps, etc. We'd be happy to get input. And look for an announcement for a GPU boot camp in October. So we'll be planning one of those. And thanks everybody for participating.